10. All right, so there's one more. Okay, so we'll just wait maybe 1 more minute for him or her. Hmm. So again, in here you can just simply add those two and then apply Ohm's law to get the current that is flowing on the entire circuit, or you can apply KVL. Okay, so either of those two will give you the same result. All right, so we're now complete. So 10 participants. So are you guys ready now? So let just give me a thumbs up just to let me know that you guys are now prepared or already in front of your computer. Okay, good. 1, 2, 3, 4, 5, 6 out of 10. So there's three who didn't respond. Anyway, so maybe they'll just catch up to us. All right, so moving on, we have another example right here. Okay, so transformation is applicable even for the circuits when which have dependent sources. Like for example, this one. Okay, so take note when we see dependent sources, we have this kind of symbol. So it's triangle. So if it's independent, it is a circle. Okay, just like this one. Okay, however, if it's triangle, okay, triangle, diamond, okay, if it's diamond like this one, most likely this one is dependent source. Okay, and if you guys are going to take a look at this one, it has a additional variable which is I. So this voltage right here is dependent onto this current right here. Okay, so this 5 volts will still vary depending on the current that will flow onto this node right here, or the I1. Okay, so for this one, so here one needs to resort to source shifting for the 3 ampere current source before applying source transformation. So this yields the circuit shown in figure 7b. So as you guys can see in here, this one is a one series connection. Okay, so you can actually like have two current source. Okay, because whatever is the current that is flowing in here is the same with the current that is flowing in here. Okay, so we just did this one, okay, into dividing that one in two to meet the condition in into transforming this current right here into another voltage source, and then another current right here into another voltage source. Okay, so those two are just the same. So once you're done in transforming this one into this one, then you can now transform this into a voltage source. So again, check if it's current to voltage, then it should be in parallel first, and then the components inside of it should be a current and then a resistance. Okay, and then after that, you will have one series connection right here. Okay, so in here, transforming those two sources into a single voltage, not single, into a voltage source. Okay, so another voltage source right here, and then another voltage source right here. So let's confirm on how did we get those values. So let me get this one, and then let's have our own solution. Labo naman nun. Okay, let's have this circuit right here instead. Okay, so in here, from current to voltage should be in parallel to series. Okay, so we are going to need the formula VIR for us to have the voltage. So I is 3 amps, and then resistance is 1 ohm. Okay, so for the first the upper uh, branch right here, we have 3 volts. Okay, and then for the second or the lower branch, So we have here 3 amps times the resistance 2 ohms. So we will get 6 volts right here. And then again, if we are going to transform this one into a voltage source, then let's just remove this one for now. Remove. Don't need that. Don't need this one. Okay. Alright, so from here, we will now have a series connection. So always take note on the uh, polarity. So we have here the resistance followed by the voltage source. So positive, negative. And then this one is 1 ohm. And this one right here is now 3 volts. Okay. And then on the lower branch or lower part, so we now have here the resistance which is 2 ohms, and then the current source voltage source which is now 6 volts. Okay, so polarity is positive, negative, and then 6 volts right here. Okay, so are we clear so far? All right, so okay, good. All right, so after transforming this one, we will now have this kind of circuit. And then you can simplify this one a little bit more or arrange this one into something like this. Okay, we now have this 3 volts and then 1 ohms going up right here. And then the middle part will stay as it is. Okay, and then the lower part will go right here. Okay, and then at the same time, as you guys can see, these 2 ohms right here and 3 amps are actually in series, so you can add them. So 2 plus 3 will give us 5 ohms. So the same with this one, so they are in series connection, so 1 ohm plus 2 ohm will give us 3 ohms. Okay, and then from here, okay, we can now transform this one again into a current source, transform this one also into a current source, and then transform this one also into a current source. Okay, and then we will just check the polarity of our current. So we will just add them. Okay, if they have the same flow of current, and if they are not, then we'll just deduct the smaller current. All right, so from here we can transform this one into something like this. So let me just get this one into a current source. All right, so let's verify on how did we get those values. So of course, for the resistance, it will stay as it is. Okay, but for the uh, sources, so from voltage to current, so it will change into a different value. Okay, so for the case number one, let's say this is your case one, case number two, and then case number three. For the case number one, we have here, so we need current, right? So I is equal to V divided by R. So voltage is 3 volts, and then resistance is 3 ohms. So 3 divided by 3 is 1 ohm, okay? Which is now this one, okay? And then you should also mind the polarity. So we have positive right here. So we should have a current that is flowing from right to left, okay? Which is now this one. And then for the next one, for the case number two, so the same, I is equal to V divided by R. So voltage is 5, okay? And then current, I mean resistance is R, 5 also, okay? But take note, this voltage right here will depend on the current, okay? But we can actually, you know, put that one aside for now, okay? We can not touch it. Will it stay as it is for now, and then we will just deal with that I later on. So 5 divided by 5 is 1 ohm, okay? So 1 amp times I. So we now have two currents. Okay. So 1 amp times I sub 1. Okay. So that's it for the case number 2. And then for the case number 3, so the same concept, I is equal to V divided by R. So V is 6 volts divided by R, which is 5. So 6 over 5 amperes. Okay. So you can convert this one into a decimal if you want, but we've just copied the entire equation, to avoid incorrect, I mean, not incorrect, uh, not accurate result. So in here, it's super accurate since we are getting everything. Okay. 6 over 5 amperes. And then again, take note on the polarity. So we have positive right here. So the polarity of your current should be going from left to right. Okay. And then from here, you already know that the case number 2 and case number 3 will be added with each other. However, the case number 1 will be deducted on the case number 2 and case number 3. Okay. So knowing that idea, we will have this result right here. So where is that one? This one. Okay. So let me just get this one. Okay. So this could be transformed into something like this. Okay. All you need to do is add if they have the same polarity of current, and then deduct if they are not the same. Okay. So in here, 6 over 5, okay, plus 1 I sub 1 minus 1. Okay. So let's add the same unit for now. So 6 divided by 5 minus 1 will give us 1 over 5 plus 1 I sub 1. This is 1 I sub 1. Okay. And in here, do we have the same? Yeah, we have the same. But we can actually have another expression, because in my case, I always eliminate the denominator. Because if you have this one, it's still quite hard to analyze. But okay, let's have another approach wherein I will eliminate the resistance. So I will multiply 5 on the entire circuit. Will it change the result? Okay, let's try that one first. So this one will become 1 plus 5. My bad. It is not possible, I guess, since we are not doing simultaneous equation. And it might affect the result since we are multiplying this one now by 5 instead of, having this fixed result. Well, anyway, let's just have one expression just like this one. Okay, so we still have denominator. We will not eliminate the denominator. So in here, in order for you to get this one, just cross multiply. So for you to have one single common denominator. So 1 I sub 1 will give us 5 I sub 1. Okay. So, and right here we still have 1 since this one is actually 1 over 1. Okay, so 1 times 1 is still 1. But in here, 5 times 1 I sub 1 will give us 5 I sub 1. Okay, and then for the denominator, so 5 times 1 is equal to 5. Okay, so that is why we now have this expression right here. All right, so are we clear so far? Are you guys still able to follow? And how did we get that expression right there? All right. So again, take note, whichever is the higher value will dominate the entire circuit. So in here, we just have a uh, higher value for this flow of current. So this one will now be deducted, and then having now a single flow of current, which is now from left to right. Okay, so once you're done with that, then you can now combine those two, the 3 and then the 3 ohms and then the 5 ohms. So as you guys can see, they are in parallel with each other. So for you to be able to get this 15 divided by 8, so okay, let's just put it directly. So 3 times 5 divided by 3 plus 5. So 3 times 5 is 15 divided by 3 plus 5 is 8. Okay, so that's how we've got that uh, resistance right here. Okay, and then for the 5 ohm, so it will stay as it is. And then from here, we can now again apply another source transformation. So from current, it can be transformed into a single, not single, yeah, single series connection. Okay, which is now this one right here. Okay, so in here we've just simply applied another source transformation. So from here, let's have our own solution since this one is quite confusing. Okay, so what we need right here is voltage. So the current right here is 1 plus 5i sub 1 divided by 5. Okay, and then multiplied by resistance, which is 15 divided by 8. Okay, so this will give us a result of 15 times 2575 I sub 1, okay, divided by 40. Can we still, yeah, so divide everything by 5 and then you will get 3 plus 5, 15, 13. Okay, am I right? 5, 10, 15 or 15? Now I'm confused. 75 divided by 5 is 15. Yeah, 15, not 13. Okay. And then at the same time, you can divide this one by 5. So you will get 8 I sub 1. So let's see if we have the same current. So there you go. We have 3 plus 15 I sub 1 divided by 8, which is the same with this one. Okay. So once you're done in transforming this one into something like this, then you can now get the total current that is flowing in here. Okay, so again, you can just simply add those two resistance and then apply I is equal to V divided by R. But in here, we have used KVL, okay, to get the I sub 1, which is also possible. So it will give you the same result. Okay, but in my case, I will use Ohm's law since that one is a lot easier. So in here, 15 divided by 8 plus 5. So of course, you have to be wise, which theorem you're going to use. Okay, so in here we will get, okay, let me just copy this one. And I will eliminate this one and then short this one. And then instead of having 5 ohms, we now have a result of 6.875. Okay, ohms. And then from here, you can now identify the current that is flowing on the entire circuit. Okay, let's see what happens next. All right, so there is no uh, other aside from this one. Okay, so let's have our own solution. Since we're using Ohm's law, let's see if it's possible. Because in here, it's super possible since, it's only dealing with one variable, in KVL. But let's try our method, or my method rather. So I is equal to V, which is 3 plus 15 I sub 1 divided by 8 divided by 6.875. And then from here, you can actually multiply this one so you can have a single expression. Yeah, are we correct? Yeah. So 3 plus 15 I sub 1 divided by 6.875. Okay, I'll just put it right here. Times 8. Okay, will give us a result of, okay, let me write this one for now. So 3 plus 15 I sub 1 divided by 6.875 times 8 will give us 55. Now, what's next? How will we know this current right here? That is actually the problem. All right, so I guess it's not possible because even though we were, we will be able to simplify the rest, the 3 plus 15, and then divided by 55, we still don't know the value of I. Okay, unless if we have KVL, having the voltage right here and then the resistance, we can add the same unit, like for example this one, I sub 1 minus 5 I sub 1. So you can have a single missing variable. Well, anyway, so let's have this one instead of my own solution, since I guess my solution is not possible. Okay. Okay. So from here we just get the correct polarity. Okay, and then the correct signage. So let's say we have, where is the correct polarity of this one? Positive minus. Okay, so in here we have a polarity of counterclockwise. Okay, since we've started with this one and then ended with a positive. Okay, so we have 3 plus 15i sub 1 divided by 8, and then minus, since this one will give you a voltage drop, of course. So minus 15 divided by 8. Yeah, and then times I sub 1, which is the current that is flowing on the entire circuit, minus, again, another voltage drop, so 5 I sub 1. Okay, and then from here, you can now separate those two into this kind of circuit right here. 3 divided by 8 plus 15 I sub 1 divided by 8. Okay, so in here, we'll just add the same units or variables, wherein we have 3 divided by 8 minus 15 divided by 8. Okay, and then what's next? Is it correct? Still 3 divided by 8. How did we get that one? Minus 15 divided by 8. We have negative 3 halves. Ah, my bad. Okay, so we cannot add those two. Okay, since this one has another variable, which is I sub 1. So that is why we cannot add those two. Okay, but in here, okay, so 15 8. What happened right here? 15 times 5 is 75 divided by 8 is 9.375. Okay, so just wait a second, guys. 1 minute. May emergency lang. All right. So going back to our discussion, okay. So let me just check what happened right here. All right. So I see. So in here, bakit laging yun? So in here, we've just simply do the math in here. So 15 I sub 1 divided by 8 minus 15 8. Actually, this one is also 15 I sub 1 divided by 8. So as you guys can see, this will give us a 0. So that is why we now have two remaining uh, expression right here, which is 3 divided by 8 minus 5 I sub 1. Okay? And then from here, we can transfer this one on the right side. And then this one now is now solvable. So just bring this one on the left side branch, and then whatever is the result, that is now the value of your I sub 1. Okay? So I sub 1 is 3 divided by 40. And then from here, you can now solve for the final total current. Okay? So just substitute that I sub 1. Okay? This 3 divided by 40 right here. And then you can now perform Ohm's law. Okay? So in here, we have to solve for the I sub 1 first before we can finally get the current that is flowing in here. Okay? All right. So did you guys get the idea so far on how to solve a voltage to current and current to voltage having a dependent source? Hello, hello. Son, which part you guys think this one is quite confusing? Well, in this case, I think everything is the same aside from having this I right here. Like, you have to get the value of I sub 1 and then substitute it right here. And then after that, you will now get the final value of your voltage. And then you can now perform again another mesh or another KVL or another Ohm's law. Okay, so you cannot solve this one directly using Ohm's law just like what I did a while ago, since we don't know the value of your I yet. Okay, but once you know the value of your I, then you can now get the uh, independent voltage right here. Okay, anyway, so yeah, that's it for this example. And then again, just a conclusion. So if we wanted to convert a voltage into a current, okay, so they must be in series connection. Okay, and then the value of your resistance will stay at the same. Okay, so series to parallel. So the same with this one, just a different polarity. So we have positive right here going up, and then positive right here going down. Okay, and then for the dependent source, okay, so you have to get the independent current first. Okay, which just like what we did right here, the I sub 1, and whatever is the polarity, so you have to follow that one. So the same with this one. Okay, the polarity. And what else? So no more. So for the sample videos, you can visit. You can visit this one. Okay, for the English videos. And then for the Tagalog video, so engineered math, I think this one came from the same vlogger, the engineered math. So make sure to visit this one. Okay. So he'll give you a lot of more examples explaining about source transformation. Okay, and then for my reference, so I think, yeah, this one also came from All About Circuits. And then for the other related articles, you can also visit those two websites wherein they are also explaining about source transformation, just another example, a different explanation, but the same concept, of course. Okay. So yeah, that's it for the source transformation. So are we clear so far? Do you guys have a question before we proceed to the next module? Question? Or if none, then you can just give me a thumbs up. And then we will now proceed to the next module. Okay, good. All right, so if you guys don't have a question anymore, then let's now proceed to delta y and y to delta transformation. So the symbol for delta is this triangle right here. And then for the y, okay, is the y alphabet, okay? So vice versa, it could be also transformed into y delta, y delta. So those two configurations. So we will discuss on how to convert delta to y and then y to delta. Okay, so without a further delay, so delta to y transformation is another extra technique for transforming certain resistor combinations that cannot be handled by the series and parallel equation. So this one is quite similar with other theorem also. So the reason why we have this concept or this conversion right here, because we cannot just simply convert that particular connection by using a series and parallel equation. So you need another approach for you to be able to get the correct computation on that one. So introducing to you delta to y transformation. So sometimes they also call this one pi to t transformation, but mostly we call that one delta to y. Okay, so this one was written by Willie McAllister. Okay, so in here sometimes when you are simplifying a resistor network, you get stuck. Okay, because we're not sure if this one is really parallel to this one is really series with this one. Okay, because we have a lot of nodes that is dealing with. Okay, so some resistor networks cannot be simplified using the usual series and parallel combinations. So this situation can often be handled by trying the delta to y transformation or delta y transformation. Okay, so the names delta and y come from the shape of the schematics. Okay, which as you guys can see, this one is an inverted delta symbol. Okay, so yeah, we now have the delta configuration. And then for the y, so it's quite obvious, I guess, since the shape of this connection right here is just like y. Okay, but for delta, it's an inverted delta. Okay, so for the delta, we have three resistors. Okay, one, two, three, and then three nodes at the same time. Okay, and then for the y configuration, we still have three resistors, but instead of having the three nodes, we now have additional one. That is why we now have a total of four nodes. So one, two, three, and then four. Okay, so yeah, and then the delta to y drawing style emphasis these are three terminal configurations, like this one, the same this one. Those two are three terminal configurations. So something to notice is the different numbers of nodes. Wherein again, I mentioned a while ago, we have three nodes right here and then four nodes on the Y connection. Okay, so the configurations can be redrawn to a square up the resistors. So this is now called the pi t configuration. Okay, but mostly this is just the original format of the problem. Okay, but once you transform this one into a delta, this is now the one that we are always focused with. Okay, so we don't deal with this kind of circuit when transforming delta to y. Okay, but sometimes it's also okay, but this one is quite confusing. Okay, so you will know later on why this one is much more conventional to use than having a pi configuration. Okay, but for the y and t, so I guess they are just the same. Okay, so we've just simply make this one a straight line. Okay, this curvy y part right here. And for the lower part, we've just added additional two nodes, okay, instead of one. Okay, so the PyT style is a more conventional drawing. So just like what I mentioned a while ago, this is the conventional. Okay, so this is the original. Okay, drawing or schematic of the problem. This is what we will always see. Okay, but we don't use this one to solve transforming this one into a y configuration. Okay, so mostly we always transform this pi into delta. Okay, so the transformation equations developed next apply to pi to t as well. Okay, in which we will always arrive with this kind of configuration. Okay, so in order for us to convert this pi into y, so you should always have a delta configuration, okay, which is now this one. Well, you can still use this one, I guess, but uh, again, it's quite difficult. So that is why I highly recommend to stick with this kind of uh, configuration, okay, which is the delta connection. Ay, nakakaikay meditas. Okay. Alright, so sorry for that. So in here, consider terminal X and Y, and for the moment, assume terminal Z isn't connected to anything. Okay. So this is just the analysis. Let's just say that for now, we don't have a connection on the Z. Okay. So if we don't have connection on Z, then we can say that the X and Y is in series connection. Okay. But I guess this will just confuse you guys. But anyway, since this is the analysis that they've come up with, on how to